So now we're going to look at examples that involve heat transfer. So we have Fourier's law that states that our heat flow is equal to our thermal conductivity times our cross-sectional area times our temperature gradient. There's two different ways to specify boundary conditions. You can specify the temperature. You can also specify the applied heat, Q, which is Ka dt dx plus beta A T minus T infinity. So we're going to assume steady state operation and that our temperature difference varies linearly. So across a thermal element, we're going to have our heat flux at our two ends is equal to our cross-sectional area times our thermal conductivity divided by our length times 1 minus 1 minus 1, 1 times our temperatures. Okay, so we're going to look at an example. We have a composite wall. It consists of 3 different sections. We have some properties. So we have, first of all, we have 4 points, right? And we have three elements. So we have some properties. We have some lengths. We're given our heat transfer coefficient. And we have the temperature on this side is 200, and we have that the heat flux on the opposite side is equal to 0. So let's start with our element level stiffness matrices. So our stiffness matrix for element 1 is our thermal conductivity, and our length for element 1 times our cross-sectional area times 1 minus 1 minus 1, 1, which comes out to be 70. We're going to do the same thing for element 2. And then we're going to do the same thing for element 3. So again, we're going to look at our continuity of our primary variable and the bounds of our secondary variables. So our temperature at N1 of element 1 is equal to T1. N2 of element 1 is equal to N1 of element 2, which is equal to T2. And N2 of element 2 is equal to N1 of element 3, which is equal to T3. We have our heat flux at point 2 is the sum of N1 and 2 of elements 1 and 2, and that's going to equal 0 since there's no heat being applied at that point. And then the tricky one here, so we have Q32, so N2 of element 3 is equal to minus beta A T4 minus T infinity. So now we're going to assemble our equations. Again, all of our elements are in series, so they're just going to sum along the diagonal. So our stiffness matrix times our temperatures is equal to our heat flux. Which, if we plug in some numbers, it's 3,500 minus 3,500 So we have 200, T2, T3, T4 is equal to Q11, 0, 0, minus 10 T4 plus 500. So again, I want to condense the system down by removing the first column and the first equations, which means I have to take my 3,500 times my 200, my minus 3,500 times 200 and bring that over to the right hand side. I'm also going to take this 10T4 and move it over to the left hand side, which is going to yield my condensed system of equations as T2, T3, T4. So the solution winds up being that T1 is equal to 200, T2 is equal to 199.58, T3 is equal to 198.67, and T4 is equal to 195.76. Then we have to go back and solve for our unknown heat flux. Q1, which is Q11, is 3,500 T1 minus 500 T2. And then Q4, which is Q32, minus 10 times T4 minus 500. That's minus 10 T4 plus 500, which is equal to minus 1457.6 watts per meter squared. So what goes in is equal to what goes out. Our last example for one-dimensional discrete systems is for fluid flow. For fluid flow, we have our flow rate is equal to minus pi d to the 4th over 128 times our viscosity times our pressure differential. So if I have a pipe, on one end I have Q1, on the other end I have Q2, I have P1, I have P2. I'm going to call my thermal resistance 128 times my viscosity over pi d to the 4th. So if my equation for my two ends, my flow rate at my two ends of my element is equal to 1 over my flow resistance times 1 minus 1 minus 1 times my pressure at my respective ends. This is very similar to resistors, thermal resistance. It's the same equation, we're just changing the variables and the numbers. So for our last example, we're going to look at this hydraulic pump network, where I would like to number it 1, 2, 1, 2, 1, 2. That's just me. So the first thing we're going to do is get our element stiffness matrix. I'm only going to write the first one, so K1 will be 1 over R1 times 1 minus 1 minus 1, 1. So let's look at our continuity of pressure. So P1 is P11, P2 is P12, which is P21, which is P31, P3 is P22, which is P41, P4 is P32, which is P51, P5 is P42, P52, P61, P6 is P62. For our flow rates, we have Q1 is equal to Q11, which is equal to 5 times 10 to the minus 4. We have Q2 is equal to Q12 plus Q21 plus Q31, which is equal to 0. The balance of forces, sum of what goes in is equal to what goes out. Q3 is equal to Q22 plus Q41, which is equal to 0. Q4 is equal to Q32 plus Q41, which is equal to 0. And Q5 is equal to Q42 plus Q52 plus Q61, which is equal to 0, and Q6 is equal to Q62. So our condensed systems equations in this case comes out to be K11, K121, K121, K122 plus K211 plus K311. Okay. This is going to be multiplied by our pressures. And this is going to be equal to Q1, Q2, Q3, Q4, Q5, Q6. So if I go in and apply my boundary conditions, I know Q2, 3, 4, and 5 are 0. I know Q1 is 5 times 10 to the minus 4. This leaves me with the problem of I have 6 equations and 7 unknowns. So in order to solve this problem, I'm going to set P6 equals to 0. This allows me to remove the 6th column and 6th equation and get rid of that Q6 that I don't necessarily know. At this point, you would plug this into a matrix solver and it would spit out your answers, assuming that you knew what your value for R is, which in this case we do not, so you'd have to solve it symbolically. So at this point, the problem is finished. That's it for our one-dimensional systems. In our next lecture, we're going to move on to two-dimensional systems by working on trusses.